Hi, hello everybody. So today we are going to cover the second part regarding the applications of crystal field stabilization energy. We will be learning 2 to 3 properties over here. All of them very important. You have got a lot of PYQs from these topics. So let's start. We have already covered spinels in the previous video. In this video, we'll be discussing about, let's start with lattice energy. First one, lattice energy. Lattice energy. Okay, so basically, what do you mean by lattice energy? When any of the ionic compound, for example, NaCl, is formed from, we know, Na plus Cl minus, they combine to form NaCl. Okay, so the amount of energy released when, please note down the heading, when 1 mole of any ionic compound is formed from its constituent gaseous ions. Constituent gaseous ions. Okay. So the amount of energy released, oh, I have not written that. Please write that as also. Amount of energy released, or it could be absorbed as well. Absorbed when 1 mole of ionic compound is formed from its constituent gaseous ions is called lattice energy. That means to form NaCl, Na plus in gaseous state plus Cl minus in gaseous state, they combine, and the energy which is involved in the combination is called lattice energy. Okay, so if the compound is being formed, lattice energy would be negative because energy would be released. Majorly, energy would be released, then only the compound would be formed. So if the energy is released, the value of lattice energy is going to be negative. Okay, so the equation is lattice energy is equal to NaZ plus Z minus by R0 into 1 minus 1 by N. You need not learn the formula. Okay, where Na is the Avogadro constant, you know. A is something called the Madelung constant. It's a constant. No need to learn all these things, but I'm just letting you know. N is also an exponent, which is a constant, which is called Bohr exponent. Okay. Now, what you actually need to know is lattice energy is proportional to the charges and inversely proportional to the inter-ionic distance. Okay, so if you have Na plus and you have Cl minus, so the inter-ionic distance, this is R0. That is important. So these are the 2 parameters directly proportional to the charges of the ions and inversely proportional to the inter-ionic distance. Okay. So what happens over here? As I said, lattice energy is expected to be negative if any compound is being formed. Okay. That is what we expect. We expect it to be negative. So more the negative value, it means more the stability. Okay. So if I have to draw, listen to this very carefully. If I have to plot, let's say, so over here I have lattice energy. And let's say we start from calcium, scandium, all in 2 plus, titanium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, nickel, copper, zinc. Let's see. This is how it is. Okay. And what do we expect? We expect that, see, the charges of the ions, and let's say it is combining with some ligand. The ligand's charge is also fixed. So Z plus Z minus is fixed over here. And what we can see is now the lattice energy is inversely proportional. Lattice energy is inversely proportional to the interionic distance. So as you move from left to right, the size decreases along a period and hence the lattice energy increases. So what we expect is a linear trend of increase is what we expect, because as size decreases along a period, the lattice energy increases. This is what we expect. Okay, but what do we get? So especially in transition metals, lattice energy of transition metal complexes. Okay, transition metal complexes. The actual value, what you see is the lattice energy which is expected, which is shown by the dashed line. And along with this, because a complex is being formed, as a result of the complex formation, there is something called crystal field stabilization energy, which we know, correct? So if the compound or the complex which is formed is negative in CFSE, it means it is stable, right? So lattice energy is negative. If a stable compound is being formed, stability will also be negative. So negative and negative, it will become more negative. Okay, let's say the lattice energy which was expected was only minus 100. But then because of the contribution due to CFSE, let's say it is some minus 0.8 delta O. Now what has happened? It has increased, correct? So it has become more negative. So what happens is usually in certain compounds, the lattice energy that you actually get is more than what you expect. And that is because of the CFSE. Okay, so the trend is not this linear. The trend is not this linear. For example, scandium 2 plus, as you know, this is D0, this is D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. These are their configurations. Okay. Now, if I write their crystal field stabilization energies along, so this is 0. If you have D1, let's say the ligand is a weak field ligand, such as F minus. So your T2G EG gap will be small. And I'm going to write in the values in such a manner that these metals in +2 oxidation state is forming an octahedral complex with a weak field ligand such as fluoride. And hence what would be the crystal field stabilization energy is what I'm going to write. Okay. So if it is D1, the configuration would be T2G1 minus 0.4 delta O. D2 would be minus 0.8 delta O. D3 would be minus 1.2 delta O. Correct? D4 would be minus 0.6 delta O. D5 is 0. Next, when you start filling D6, the same pattern will repeat. Minus 0.4 delta O, minus 0.8 delta O, minus 1.2 delta O, minus 0.6 delta O, and 0. Why is this happening? That is because we have considered to be a weak field ligand. The trend will change if it is a strong field ligand. What we have considered is it is a weak field ligand. Okay. So calcium 2 plus whatever lattice energy is expected, along with that you have to just add the normal CFSE value, which is 0. So the expected value and the predicted value are the same. because CFSE is 0. Similarly, for Mn plus 2 also, as there is no extra CFSE, anything plus 0 would be the same number. So for manganese also, manganese plus 2 with a weak field ligand, the lattice energy would be as expected. Similarly, for zinc 2 plus also, it would be as expected because there is no CFSE that is contributing the lattice energy. But let's take the other cases. Scandium. You have some value of lattice energy and to which you're adding more. Let's say it was minus 100 and you're adding more minus 0.4 to it. Understand that negative sign just denotes stability. Do not think that this is a positive axis. Why are we writing it towards up? No. You're taking the modulus. Okay. We are taking the modulus. So when you take the modulus, negative denotes more stability and 100 plus 0.4 delta O is what you have. So let's say it is somewhere over here. Titanium, you're making it even more stable, higher. Vanadium minus 1.2, even higher. Got it? Chromium minus 0.6, somewhere over here. Manganese meeting the expected value. D6 again, whatever is expected to which you add more stability. So it goes up. Cobalt goes up. Nickel, it goes further up. Copper, it comes down. And then zinc. So the actual trend is not the black dashed line. Instead, you get a line like this. Can you see the trend? This is the actual trend of lattice energy for the complexes of transition metals in +2 oxidation state with a weak field ligand, important, forming octahedral geometry. This is a trend. Okay, so if you expect the normal trend, if you just expect the normal trend, you feel that the highest lattice energy will be for zinc because this is a trend that you expect. The stability of the zinc complex would be the highest. But actually, when CFSE is also considered, it's not zinc. You can see the highest point is for nickel. Nickel is the most stable one, right? Nickel is the most stable one. It is at the top. Okay, so it's not zinc. The highest lattice energy of a transition metal complex in 3D series is that of nickel, nickel plus 2. Nickel plus 2. Okay, so I hope you understand this. So I'm just summarizing it again. Lattice energy is something which is proportional to the charges divided by interionic distance. Now, if you just expect that equation to be valid, what we get is a straight line and increasing trend of stability of lattice energy. Lattice energies are generally negative. They are generally negative, but then we have taken the modulus value. Negative sign just denotes the stabilization, means it is stable, that's all. Okay, now what we said is actually lattice energy is not the only contributor. CFSE also contributes, which is also negative. So in totality, lattice energy is negative, to which you add CFSE, which is also negative. So as a whole, it becomes more negative. So how much more is shown by the violet dots. Okay, so calcium, manganese, and zinc align with the expected value because CFSEs are 0. While for others, you see a trend like this, out of which nickel complex shows the highest lattice energy. Okay, I hope you're getting it. Okay, now the same thing in Huhe. Again, there is another graph of lattice energy or hydration energy, I cannot recall, wherein they have tried and they have put in a graph for, we'll try it along. Let's try. I'm going to give you a task. You pause the video, try it out and check. Oops. Okay, let's say you have modulus of lattice energy, and instead of +2, what you have now is +3. Scandium +3. We'll start from scandium +3 because that is D0. Okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. This is how it is. Right. Okay. Now I want you to write or to draw the trend when these metal complexes form octahedral complexes with a weak field ligand. What is it that you expect? You expect it to be linearly increasing because as you move from left to right, the size reduces. Lattice energy and size are inversely proportional. So you expect it to increase it like this, but that is not the case. What happens? This is D0, this is D1, D2, D3, D4, D5, D6, D7, D8, and D9 is what you have. Okay. Now I want you to fill in the electrons in T2G, EG levels, and I want you to draw the trend. So D0 means T2G 0, CFSE would be 0. Here you get minus 0.4 delta. Here minus 0.8 delta. Okay, let me. Minus 0.4 delta O, minus 0.8 delta O. Here minus 1.2 delta O, minus 0.6 delta O, 0. Minus 0.4, the trend repeats, minus 0.8 delta O, minus 1.2 delta O, and then minus 0.6 delta O. This is the actual trend. So for scandium, it is the same as expected. For Fe+3, which has got a D5 configuration, CFSE 0 also meets with the expected value, while others will show a shift because there is a contribution due to CFSE. Right? What would be that? Titanium 3 plus, slightly higher. Vanadium 3 plus, higher than that. Chromium 3 plus, higher because minus 1.2. And then manganese +3, a bit lower. Correct? Over here also, higher, higher, and higher. And then you decrease like this. Okay. So this is the actual trend of +3 ions that you see. So if you can see over here, D8 for copper +3 shows the highest lattice energy. Okay. So this is when you have a weak field ligand. Now, along with this in Hue-He, they have plotted another plot wherein the lattice energy is depicted for these species with a strong field ligand. You try that as well. Strong field ligand. So when you have a strong field ligand, you can understand that T2G EG gap will be huge. And now the CFSEs would be different. How different? This would be 0. This is minus 0.4 delta O. This is minus 0.8 delta O. This is minus 1.2 delta O. Here, be careful. The fourth one won't jump to EG. Instead, it will get paired up in T2G itself. So this would be minus 1.6 delta O. Right? This is 2 delta O. This is 2.4 delta O. And then you have 2.4 minus 6 because now it enters EG. I hope you're understanding. Okay. So what you have over here is minus 1.8 delta O, minus 1.2 delta O, and minus 0.6 delta O. This would be the trend. Okay. So over here, you can see that the lattice energy, scandium as expected, titanium a bit higher, vanadium, higher, chromium, higher, manganese, even higher, Fe plus 3, even higher, cobalt plus 3, the highest. Because now you have a strong field ligand. The electrons are just entering the T2G orbitals and they're not entering the EG. And then finally, nickel lower, copper lower, zinc even lower. So this is the trend that you see for plus 3 metal ions in combination with strong field ligand forming octahedral. Okay, so you might get questions like this. I hope the concept is clear. So lattice energy combines with CFSE to give alternative values of stability and whose trend is what we have discussed. Now, if this is understood, rest everything will come with a flow. Okay. For example, the next one is hydration energy. Hydration energy. What is hydration energy? Let's write the definition. When 1 mole of ionic crystal is dissolved in water, H2O molecules get surrounded around the ion and releases some amount of energy, and that amount of energy which is released is called hydration energy. Okay, so when you take some crystal, let's say NaCl, and if you put it in water, we know that it will dissociate. And the moment it dissociates, what happens? There would be a formation of a solvent cage. That is, Na plus would be surrounded by H2O moieties like this. Okay, why? Because oxygen is partially negative. And Cl plus will be surrounded by H2O like this. Because hydrogens are partially positive. So there would be a formation of a solvent cage. And as the formation of the solvent cage happens, there is some amount of energy which is released. And that energy which is released is called hydration energy. Okay. Here also, the trend is the same. Hydration energy is actually energy being released. So this is actually negative, which depends on charge and is inversely proportional to the size. Okay, it is directly proportional to the charge of the ion and inversely proportional to the size. So the actual hydration energy that you observe for transition metal complexes, coordination complexes, what you see is equal to the hydration energy as expected. You will be expecting something plus CFSE. So hydration energy is negative, CFSE is also negative. So as a whole, it becomes more negative. Okay. So I hope you understand that. So the trend will be as similar to that of lattice energy. Not drawing it again. Should I? It's going to be the same. See, this is the same graph that you're going to get. Same graph. You can just write it as a trend same as lattice energy. That's all. See, here what you can see is the hydration energy is inversely proportional to the size, right? So what do we expect? We expect that as the size reduces from left to right, hydration energy increases is what we expect. But over here, because of the contribution due to the CFSE, Apart from the normal hydration energies, there would be additional CFSEs. Now, what we have considered over here is M plus 2 in combination with a weak field ligand like F minus. So this would be the trend. Same trend as that of lattice energy. The concepts are the very same. Okay? Very same. It's just one is hydration energy, the other one is lattice energy. Both are forms of energies which is being released. Lattice energy is when the ionic compound is being formed. Hydration energy is when the ionic compound is put in water. Okay? So I'm not redrawing the trend for +3, strong field and all. You have got the concept means it will be clear. Okay. Next one is size. Size. So, as we already saw, that lattice energy is inversely proportional to size, right? Or hydration energy is inversely proportional to size. We saw that. Correct. So the trend that you see in lattice energy, the trend for size would be the exact opposite. Okay, I'll draw this so that you can understand. There are other ways to explain this as well, but then I'm not confusing you. Yeah, this one. Okay, let's say you have size R. Okay, and we start from calcium +2, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay. Now listen, what we saw, what we expect is as you move from left to right, your size along a period decreases, right? Your size, this is a linear trend that you expect. As you move from left to right, your size decreases. This is what you normally expect. But that is not the case. Because of the CFSE, we already saw that lattice energy, hydration energy has got a M-like trend. M. Up, down, up, down. This is how you see it. So the size is inversely proportional. So the trend will also be the ulta. Calcium, manganese, and zinc will be as expected. Others will be the exact opposite. Like this. Okay. So for lattice energy, hydration energy, you got a M-like trend. Here you're getting a W-like trend. When you have +2 ions in combination with a weak field ligand, is the case forming octahedral geometry. This is the trend that you see. Okay. I hope you get it. I need not explain it, right? There are other ways to explain this as well, but then it might confuse you. That's why I'm not explaining it in that way. I think this is sufficient. Okay. All right. Yeah, a few more things. Next, stability of the complexes. So we said about lattice energy, hydration energy, size. The next one is stability. Stability of complexes, and that is obvious. Okay, let's say you have CO, H2O 6 times 2 plus. And you have CO, H2O 6 times 3 plus. Both the metals are the same, ligands are the same, only difference in oxidation state. You have to find which one is more stable. So what do? You find the CFSE, that's it. So here, what is the value? Here, Cobalt is in +2 in combination with a weak field ligand. So you have T2GEG. Cobalt 2 plus is a D7 configuration. So you fill 1, 2, 3. Fourth one will jump over here. 5, 6, 7. Okay, so the configuration is T2G5EG2. Your CFSE value will come out to be minus 0.8 delta O. Cobalt +3. I've always told you be careful when you have cobalt +3. Water along with cobalt +3 is a strong field ligand. You have D6 and the configuration is 1, 2, 3. Because it acts like a strong field ligand, the electron cannot jump to EG. It will get paired over here. So T2G6, EG0, CFSE is going to be minus 2.4 delta O. CFSE is higher, means stability is higher. Okay. That's it. So you get to know about stability. Stability of the complex. Next, you can also get to know about the oxidation potential. Oxidation potential. Oxidation potential. Let me take the same case. Okay, I'm not repeating it. Let me take the same case. COH2O 6 times 2 plus. We found that the CFSE of the system was how much? Minus 0.8 delta O. And the other one was COH2O 6 times 3 plus. We found that the CFSE over here is minus 2.4 delta O. Correct. So oxidation potential is the capability of converting this. So if you oxidize this, what will happen? One electron will be lost and this will become H2O 6 times 3 plus. This is oxidation. What will happen to the second complex if you oxidize it? CO H2O 6 times 4 plus. Can you see? 2 plus has become 3 plus upon oxidation. 3 plus has become 4 plus upon oxidation. Oxidation is loss of electrons. So which one would be feasible? So this is highly stable, very stable. So it won't give its one electron for oxidation. This won't happen because it is already very stable. While this one, comparing to this compound, is less stable and can go oxidation. So this is how you predict the oxidation potential. Okay. All right. Next, we can also predict the interconversion of complexes. For example, let's say you have NiH2 6 times 2 plus. Okay. You do some substitution with chloride and it becomes NiCl4 2 minus. And to this complex, you add water, it becomes the complex on the left. Okay. So the left one, when you add Cl minus, it becomes NiCl4, 2 minus. And to this complex, if you add water, it becomes NiH2O 6 times 2 plus. You have to see which one is more feasible. The forward reaction or the backward reaction is what you have to check. Okay. So for that, what will you do? On the left, you have nickel +2, water ligand, which is weak field ligand. Nickel +2 is D8. So you have to fill T2GEG according to D8. 1, 2, 3. Because it is weak, 4 will jump. 5, 6, 7, 8. Okay. So the configuration is T2G6, EG2. CFSE is minus 1.2 delta O. This is how stable it is. On the right, you have nickel plus 2. Cl minus is a weak field ligand. Again, D8, but the coordination number over here is 4. So you have E at the bottom, T2 above. So 1, 2, 3 can easily jump in all tetrahedral complexes because the splitting would be small. 4, 5, 6, 7, 8 is what you have. So you have E4, T2, 4. That is what you have. E4, T2, 4. And the CFSE corresponding to this state is 1.2 minus 4. This is minus 0.8 delta T. Minus 0.8 delta T. Understand that you cannot compare these two because one is in delta O, the other one is in delta T. You cannot compare. Okay. So if you have to compare, you have to make them in common terms. How do you make that? Minus 0.8 into 4 by 9 delta O. Correct. That's how you convert delta T to delta O. Now, once you solve this, you will get it as 0.35 delta O. Okay. So, on one hand, you have minus 1.2 and the other hand, you have only minus 0.3, which means the octahedral complex is very stable. The octahedral complex upon addition of chloride to form this tetrahedral complex is not that feasible because see, the stability of the complex is way, way, way less. So, forward reaction won't be feasible, but the backward reaction would be feasible. Why? Because backward reaction is where your nickel tetrahedral complex upon addition of water is becoming an octahedral complex whose stability is very high. Whose stability is very high. Okay. So I hope the applications are clear to you. Okay. Yeah, so with this, we have come to an end of crystal field stabilization energy and its application. The next class, we'll be discussing about John-Teller distortion. Very, very, very important John-Teller distortion. Again, one of my personal favorites. Okay, so we'll be releasing one assignment probably, and then let's see. Okay, so thank you.